And so now on to hydrocarbons. This is just a basic introduction to some of the easiest of the organic naming. So hydrocarbons are compounds that contain just carbon and hydrogen. Okay, pretty easy to remember, hydrogen and carbon. We're going to talk about three different classes of those. They're the alkanes, the alkenes, and the alkynes. You'll notice that they have a formula that goes associated with it. So that's going to be telling me how many, if I'm given a certain number of carbons, it'll tell me how many hydrogens I would expect. So let's look at the first example of C3H8, which happens to be propane. Okay, it has the suffix of ane in there. So I see that I have twice as many hydrogens plus two more than I have of carbon. So let's form a catenation, first of all, of my carbons, and let's see where those 8 hydrogens would go. 1, 2, 3, 4, 5, 6, 7, 8. I know I only had 2 around here because I'm still following the octet rule. I don't even have to draw the hydrogens on here because I know it's a hydrocarbon and it follows that example. Tetrahedral, 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 1 to 9.5 for all the angles. Since it is hydrogen all the way around and no electron heavy or anything like that, these would be non-polar molecules. Okay, so then let's look at what would happen with when we're predicting how many hydrogens would be in a larger compound. Okay, now first of all, the really slow and way I do not want you to do it is to actually draw it out. I've had people do this in the past. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. You see how ridiculous that gets when we do all that. If you were to fill in all of your different hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 4, 5, 6, 7, 8, 9, 30, 31, 2, 3, 34. Ugh. That's not the way you want to do this. Okay, we want to pop that equation in. So 17 times 2, that's 14. So that's going to be 34 plus 2 more is 36. Okay, so I would end up with C17H36. That's a lot faster, more efficient. I know it's going to be the same. I don't even know if I counted those all up right because I got lost in all that mess. Okay, so those are your alkanes. Now let's take a look at our alkenes. Alkenes are just saying 2x. There's twice as many, exactly twice as many hydrogens as there are carbons. So how can that be? If I combine my form a catenation with my carbons, first of all, and then I have this for the basics, and I only have 4 total hydrogens. 1, 2, 3, 4. How could that be? Oh, I must have a pi bond in there. So if I was going to clean this up, if I saw it fit the pattern, here is where I'd automatically just put in a pi bond, a double bond, and then I'd have my hydrogens sticking here and here. This still counts up as 3 and 0, so that's a trigonal planar. 120 is the angle. It would be nonpolar. So if I take a look in 47, well, what's 47 times 2? 14, so that's 8, that's 94 total hydrogens, so this answer would be 94. Do not try to go and fit in all 47 carbons, okay? That's just ridiculous, and know that this first, we always assume that it's going to be in the first place. If we're going to put that double bond in another place, okay, say for example, it's not in the first spot, it would go, maybe it's going to be over here. We would have to tell the reader that, and this keeps on going for all 47. We would say this is the first spot, second spot, third spot. So we would have some system of indicating that my double bond, that's what alkene means, is one double bond is in the third position. And so if this had a name, for example, this is going to be ethene. Okay, E-N-E, and I'll get into naming in just a second. Eth means 2, so ethene, I might say it's 2. Well, actually, we'd have to go 1, 2, 3, 4, 5, 6. So hexene, but it's in the third spot. So we would call that 3-hexene. If you just see hexene, we would assume it's in the number 1 spot. Okay, so that's what all of that means when we have the numbering system in place. Okay, we would refer to that, if the number is in a different spot other than the first position, we would refer to this as a conjugated system. Okay, so again, we would see hexene, which means hex means 6, and I'll get to that in a moment. Ene means a double bond. If I just see hexene, I would automatically put it in the first spot. But if I see 3-hexene, it is an example of a conjugated system. I would put a double bond here. Now, we could actually have a 1,3-hexene. That's another example of a conjugated system. It would violate my rule of just 2x because 1,3 means ene means a double bond in the first and third spots. So here and here, do that first and then plug in your hydrogens to see what you get. Notice that I have 2 already taken care of, 2, 4, 6, and 8, 2, 4, 6, and 8, 2, 4, 6, and 8. I'm putting them up and down just for fun. 2, 4, 6, and 8. 2, 4, 6, 8, 2, 4, 6, 8. Okay, so notice what happens if I do that. I'd have C6. If I recognize this term, I'd see it's a double bond, but it's in a couple of spots. What's the result? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's not going to be a 2x scenario. We're going to lose 2 because I have a double bond in a couple of spots. Okay, so that's just a conjugated system and how that might work. We have the example of how to do alkenes. Let's look at the last example of alkynes. Alkyne follows the example of 2x minus 2. How does that one work? 1, 2, 3, 4, 5. We have only 8 hydrogens to fit in. The reason for that is we have a triple bond right at the beginning. So watch what happens. Here we have 2, 4, 6, and 8. Around this carbon, we've already got it full. 2, 4, 6, 8. It's already a full octet. This carbon, 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, and 4. So the result is hydrogen 1, 2, 3, 4, 5, 6, 7, and 8. So that's how we fit this 2x minus 2 configuration in. And notice that we have a triple bond. Again, we could have a conjugated system where we move it over. Watch where you put your hydrogens in. Also look at how this would count up for angles. This first carbon would have 2 shared pairs, 0 unshared. Remember, we don't count the pi's. I can't emphasize that enough. That only brings it in tighter. That doesn't influence the shape. So this would be referred to as 2 and 0, 2 and 0, and the rest are going to be 4 and 0. Okay, so the shapes of those are going to be fitting in there as well. Now, this last example to finish it off, if it fits in the 2x minus 2, don't draw them all out. Just say 10 times 2 is obviously 20, minus 2 is 18. That's how you figure out those. Now, you notice that a couple times I threw in terms like propane and hexene and things like that. That's because if you see a hydrocarbon, we have special naming rules. Another set of things that you have to remember. Now, the first one, if we have an example of like CH4, obviously it's an alkane with 1 carbon, okay? 2x plus 2, so 2 times 1 is 2, plus 2 more is 4. All right, so we've seen this example a lot. We call this guy methane. So you can see how these things work. It still fits this example of anes, and we see it have only 1 carbon in there, meth. Okay, so that's the prefix when we see 1 carbon. We're going to name these according to how many carbons are present. So meth, eth, prop, bute, not but, it's bute. Then we go pent, hex, hept, oct, and non. And then it goes into dec and all those other things. But these are all the prefixes. Now, the suffix, well, that depends on which version are we referring to. Is it an ane, is it an ene, or is it an eine? Okay, so just count up how many are in there. I always think of these first 4 as Mikey eats peanut butter. Okay, Mikey eats peanut butter. That really helps. Pent, hex, hept, and all that. People usually remember those. Now, there's one more thing that can actually happen in hydrocarbons, and that's that they form an actual ring. So what happens if I have 6 carbons, 1, 2, 3, 4, 5, 6, and they're all combined this way? Well, here I see 6, so that's hex. They are all single bonded, so it's ane. But notice, if I form them all up in a ring, which they commonly do, we see that the number of hydrogens, if I were to count them all up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, not 14. So how do we know as a reader that C6H12 is actually all single bonded versus an alkene with a double bond? Well, the reason we see this is because they're all formed together. So I throw a prefix up in front called cyclo. A circle. It goes all the way around. That tells the reader that all these carbons are going to be bonded to each other. And then we plug in our hydrogens. So when you see terms like cyclohexane, you have to draw it out, then count up your hydrogens as we go. And so we can get really crazy with this, and we can just simply do this. Well, what does that mean? That means that we have a carbon here, here, and here. Result, I have 2, 4, 6, and 8, 6, and 8, 6, and 8. So I have 1, 2, 3, 4, 5, 6. I have C3H6. This would be, because they're all bonded together, that's what the triangle actually showed in the first place. This means that it's going to be cyclo. And if we remember, we have 3 carbons, okay, 3 carbons. Mikey eats peanut butter. This would be eth. Oh, I'm sorry. This would be prop. And they're all single bonded, so it's ane. What if we threw a double bond in here? Well, that just changes the suffix, doesn't it? That's going to be now propene. Or maybe it's triple bonded, okay? So then we'd have ine. So we could do all those things, just plug in your hydrogens and you'd be good to go. So that is a cyclo arrangement of the hydrocarbons.